Well, good morning, everyone. Where shall we get started? We're going to begin a new chapter today. The first chapter, or the first part of chapter 9, is about content. It's about vocabulary and symbols, and it's the whole chapter is sampling distributions. But we are just going to do first the introduction. Now, quite a few of these things are the same, and you've met the terms before, but they're going to look at them again. So there are two main different types of places or ways that you collect your data. There's population, and then there is a sample. And when you take a population, right, basically, you get a census. This is where you ask everyone. And then a sample, it's called a sample, which is a little bit hard. And that you ask only some. And the people you ask have to come from the population, or it's not a real sample. So we've heard of population, and we've heard a sample. There are two types of pieces of information that we get. There's proportions, and then it means. And in a sample, the two types of information you get are also proportions or means. So a proportion might be, if you did a census, right? If you asked everybody in the population, do they like Pepsi? And the answer you might get back is that there's, I don't know, 40,000 people who live in this city, and 33% of them like Pepsi. A proportion is a kind of question where the answer is either yes or no. Are you in favor of the death penalty? Yes or no. Are you in favor of abortion? Yes or no. And proportion then ends up being written down as things like 30% like Pepsi or 0.3 like Pepsi. And you can also have, I guess, it's likely, but I guess it could happen, you could get 300 out of 1,000. That would only really happen if the population was tiny, which most of the time they're not. And when you do means, you get things like, you asked everybody in Bremerton, and you found out that their mean age was 37.1. Or, you know, how much are they in debt? How old is their car? Right, and the average age of a car is 3.9 years. The mean is the one where you add them all up and divide by how many, and the proportion is top guy, those who said yes, bottom guy, the total number of people. Now, when you're over here, you get exactly the same kind of things going on. Difference is that when it's a sample, you don't ask everybody. You only ask maybe 200 people in Bremerton, and you find out that 27% of them like Pepsi. Or you could write it as 0.27, or you might write it as 27 out of 100. And then you do the means, and you find out that it's 34.9. Now, when you do proportions, back to these guys again, when it's a proportion and the information came from a census of a population, we call these guys P. P for proportion. And when it's a mean, we use that funny little sigma. Do you remember that? Mu, I should say. You remember that funny little guy? Pronounced mu. When you get a proportion from a sample, you call it p hat. That's what we call this out loud. P hat. And when you have a mean, oh, can anybody remember the symbol that you use when you get a sample mean? We use the word or the Greek letter nu for a population mean, but what do we use it when it's a sample? What does it look like?
Sigma, was it?
No, but you could try. Any other ideas? You might know the symbol, but you just called it sigma. X bar. So you see that little X with a line above it? It means the sample mean. So recap, population is everybody. If you collect information from a population, when you ask everyone, it's called a census. There are two main types of information you're going to get. One of them is the proportion, and you will see P equals. So if you ever see a question and it's talking about things and it says P equals 0.3 or P equals 30%, you know by the fact that they called it P equals, that number is a population number, right? It came from everybody in the population was asked. It came from a census. If they use a term P hat, you know it's a proportion. And you also know, because they use the symbol P hat, that it came from a sample. And that's where they only ask some people from the population, right? If it's a mean, they'll call it X bar. So if you see X bar, you also know that that's a mean, but the mean came from a sample. We call these guys, P and mu are examples of them, these are called parameters. Over here, P hat and X bar and any other number that you might use, those are the two common ones. Those are called statistics. So there's our vocabulary so far. If the information you collect is from a population, like P or mu, we call these things parameters. These are examples of them. And if they come from a sample, will be P hat and X bar. So far, so good. Just some symbols and vocabulary. The first section of homework is pretty much just getting you to do that type of thing. So let's have a look. So in question 1, in each situation, explain whether the value given in bold print, so in this case it says 71%, is a statistic or it's a parameter. So you have to read the story to decide, did this 71%, did it come by asking a sample of people, or did it come from a census where they got the answer by asking everybody, right? So a polling organization samples 1,000 adults. I think I don't really need to travel very far. Do you think even before the end of the sentence, I know where this is going? Agreed? Since they had a sample of 1,000 adults, what's that 71%? Is it a statistic?
Yeah, it's a statistic.
So which one of those two is the right sentence?
Second one.
Agreed? Now you can imagine what that's going to look like in a test. Isn't that one of those multiple choice ones where one of the 4 is the right one? Now, keywords, if you see the word sample of, isn't that going to be coming from the sample side, right? The numbers you're going to get are statistics. And later on, the numbers you're going to get are going to be called P hat and X bar, because they might ask you, should this be called P hat equals 70% or whatever? The other word to look for is that. If you see the word census, doesn't that mean they asked everybody in the population? So in the year 2010 census, the US Census Bureau, and there you get the word twice, found that the median age of Americans was 37.2. And since it is a number that came from the entire population, it's a parameter, and it would be that one. So do not overthink these questions, right? There's 4 choices and one of them's the right one. Now let's do D. A writer wants to know how many typing mistakes there are in a manuscript. So he hires a proofreader who reads the entire manuscript and finds 13 errors. Okay. Is 13 a statistic or a parameter?
Parameter.
Right. He read the whole book, right? He read every word for spelling mistakes. So that makes it parameter. And aren't parameters always a population value, right? They're never going to be the second one. That's just to throw you. Okay. A polling station plans to sample 1,000 adults, right? So we know we're talking about a sample here. And they want to do it to estimate the proportion of Americans who think crime is a serious problem in this country. In the context of this poll, explain the difference between a statistic and a parameter. And what is the parameter of interest to the polling organization? And what will be the statistic? Well, the parameter then is the proportion who think that crime is a serious problem in the population. You see, at the end of the sentence, you realize that they're talking about a parameter, aren't they? Very often you have a question that you want answered. Like, I wonder what the average age of Americans is. Or I wonder what percentage like Pepsi Cola, right? Whatever. That's the parameter of interest. The statistic will be the proportion of the 1,000 adults in the sample. So essentially what happens is you've got some question you're interested in, like, I wonder what percentage of Americans think crime's a problem. Well, you can't really ask everybody. If you could, that would be a census, but it's pretty impractical and expensive to do it. So what you do instead is, don't you ask 1,000 people or 10,000 people or 500, whatever you decide. And if 42% of them say that they think crime's a problem, can't you then say, well, the real answer is probably going to be close to 42%, right? If I ask the question well and my sample's big enough and I don't get, for want of a better word, really unlucky, won't the sample statistic be really close to the parameter? That's why we do samples, right? We ask some people the question we want to ask everybody. And we hope that the answers we get from that some people, that's our sample, are pretty representative of what the entire population would do. And so we can make that as a way to predict what we believe the entire population would be. And where are we now? This will be a proportion of 1,000 Americans who think that crime is a serious problem, and its value will be known after the poll is taken. The statistic will estimate the unknown parameter. So we use a statistic, right? Or, out of the 1,000 people, how many said that crime was a problem? We use that number and we use it to predict what we think the parameter would be for the entire population. Now let's see what this one is. Some stockholders want to know whether the mean salary for the male employees in the company is higher than the mean salary of the females. Okay, for equitable, I guess. The company allows them access to the salary information, and here's a very interesting word, all. Doesn't that mean this is a census then? They got all the information. They didn't say, well, we looked at 50 people at random and found out what their salary was, right? We went to the records, we looked at everybody. And there's 100 males and 100 females, which I think they just did to make the question simple. And the mean salary for the men was 51,000, and it was only 49 for the females. Interesting. Couple of thousand, well, 1,500 difference. Are the mean salaries in this example statistics or parameters? Okay, in that story where they went into the records and they found out the mean salary, statistic or a parameter?
Parameter.
Right, came from everybody, right? And then when you do parameters, then you look at which one of these. Where is the parameter? Yeah, the one we're going to use is that one. And why that one? Because they used the entire population. Now, on the basis of this information, the difference between the males and females, can the shareholders determine the mean salary from males in the company is higher than the mean salary from the females? Right. And the answer is yes. They asked everybody, so it's true. Suppose they didn't do everybody. Suppose they only got the salaries of 10 men and 10 females, and the same information appeared. The reason why that's not guaranteed is that if you do a sample, don't you get a different answer each time? You ask different 10 people, the answer varies a little bit. And so that wouldn't you wouldn't be able to do it for certain. You could make a prediction that it was true, but you wouldn't know for certain. So let's turn this thing on its head. It is actually quite right, if you look at national data, and the government's got really big data sets on this, that women do tend to get paid, on average, less than men. Right? That's a statistical truth. But the leap from that piece of information to what I'm about to say isn't actually provable or valid. I could say, right, let's make it up. Men get paid on average 10% more than a woman does. Just making that number up because I don't know what the real one is, but it's significant. That means that America is a sexist society, and we just pay men more than women, and that's unfair. Now, you might think, well, that sounds reasonable. Right? Why are men getting paid more than women? Well, if all things were equal, shouldn't they get paid about the same? And I believe, at least it's true in Britain, and I believe it's true in America, that if two people are doing the exact same job, right? It's the exact same job. They need to get paid the same amount of money. You can't work in a factory and assemble radios, and the person next to you is a guy and he's assembling the exact same radio, right? And none of you are bosses, right? You're just workers. It's illegal. Is that also true in America? Right? You sue people if they do that. So what are the problems here? Why is there that discrepancy? Now, I guess it still could be true that Americans just don't pay women the same amount of money. And that's one possible solution. But they have looked into the others. It's quite interesting. Women lumberjacks get paid the same amount of money as men lumberjacks. There are just an awful lot of men lumberjacks, aren't there? Not many female lumberjacks. Men nursery, right? Kindergarten, nursery people, men, they get paid the same as women kindergarten people. But aren't there an awful lot of women who do kindergarten jobs and not many men who do kindergarten jobs? lumberjacks get paid a lot more money than kindergarten people. Can you see how that would have a distortion on the average salary of men and women? A lot of jobs that men do can get paid more than women. But one of the reasons for that is that dangerous jobs, not exclusively, but dangerous jobs tend to be done by men and less by women. Is your typical oil rig guy in the North Sea, in Britain at least, is he a man or a woman? He's a man. Oil rig jobs are very well paid. They're also quite dangerous, aren't they? And so when you look at the data, why is there a discrepancy here? It's more of it is to do with the jobs that men and women do. And there's some, not very good, but there is some evidence that suggests that men like stuff and women like people. And so women tend to get into professions that are very caring and very, very worthwhile, but with some exceptions are not paid as much, right? And men like to do engineering things or dangerous things, and they tend to get paid more. And that is one explanation for that. So what am I getting at here? You can have a fact, and then you can make a conclusion based on that fact that may or may not be true. So be careful when politicians tell you some numbers and then say, this is proof of whatever it is they want to prove to you, right? There can be other reasons behind the difference between any two sets of values. Okay, moving on to 4. We've got p hat or p. Now, remember, p hat means the number came from a sample, right? It's a proportion from a sample. And p is a proportion from a population. So in question A, the proportion that smokes in a randomly selected sample of 100 in the 10th and 11th grade. Would you agree that that's a p hat number? And it's kind of hard to hide these questions, isn't it? Because isn't there probably going to be the word sample somewhere? Right. So it's correct, and it is a sample proportion, right? And there's another one, there's another one. Okay, this one is going to be an X bar or a mu. When you see those symbols, doesn't it mean you've collected the mean, right? You found 200 people and found their average, right? The mean. If it says X bar, it's a sample. And if they use mu, it's a population. So a university administrator determines that the mean age of all students at the college is 20.1. What's that? An X bar or a mu? There is a word in there that kind of gives it away.
X bar?
The word that gives it away . Now, we don't know how he determined it, but maybe he went to the records and looked at every single student, right? Can you see the word all is the clue, right? They asked everyone. So when you ask everyone, isn't it a mu? Mu is a population, came from a census. And so you're going to do mu, and it's a population mean. Okay, here's a slightly longer version of this question, this type of question. So they took a random sample of 300 parents in a school district. 110 of them supported a controversial new education program. whatever that means. The purpose of the survey was to estimate the proportion of all parents in the school districts who support a new program. Well, it would be nice, and I guess it happens, that the school district, well, let's say it's a sex educational program, right? That very often gets an awful lot of strong views one way or the other. And they want to know whether this new sex education program has got enough support so they could do it, right? And so I'm assuming the school district randomly got 300 parents, and 110 of them said, yeah, we like this, this is a good idea. The opposite of that isn't 190 of them said, I don't like the idea, don't do it. I mean, because there's only yes, I like it, or no, I don't. That's typically the dichotomy that we use here. And so it says, what is the research question of interest? Well, the second sentence kind of tells us what that is. The purpose of this survey was to estimate the proportion of all parents in the district. So it would be the second dot, right? That's why they're doing this. They want to find out what all of them want. The population parameter then is the proportion of all parents who support this new program. What should we use for this one? Shouldn't it be the guy there? P. Isn't this a proportion? It's not an average, it's not a mean. And what's the value of it? Well, based on what I can see here, it's 110 out of 300. And that has to be rounded off, so here goes. That's 0.367. So about 37% are in favour of it. What is the appropriate statistical notation symbol for this estimate? Which one of these four guys do you use when you only get the number from a sample, in this case, 0.367?
Isn't it X bar?
Is it X bar or is it something else? This is a proportion. So you could have X bar, but that would be for the mean. Right?
Oh, isn't it P hat then?
It's P hat. I try and remember proportion starts with a P, because the two symbols are just symbols, right? You know, you don't have any context unless you do that. Are we good so far? Do you feel this section basically is just going to ask you lots and lots of examples of, is this a parameter? Is this a statistic? What symbol do you use? X bar or P hat or mu, or, you know, or so on. And that's what that one's about. Okay, let's do this one. Explain what the symbol P hat, mu, etc. would be used to represent in each of the following. So this one, the mean of a sampling distribution of the sample menu. Okay, that's us reached the new stuff. So what we've been doing today is really just a quick vocabulary symbol thing. So this thing called the sampling distribution, for some people it's a little bit hard to get their head around, but after a while it becomes pretty straightforward. So I'm going to do a little pretend story. I am interested in finding the proportion of Scots people, we'll say adults, who get drunk at least once per week. Now, you can define what drunk is and so on, but we'll assume everybody knows what they mean when they say they're drunk. And the answer, the real answer, right, the population answer could be, let's pretend we knew it, which we don't, But let's suppose it was 12%. Let's suppose somehow somebody, Bill Gates, gave us a lot of money and we asked every single person and it was 12%. Right. Now let's pretend now that we didn't know it was 12%. And what we did is we got a sample. And so we go and we find 100 Scottish adults and we asked them, and we're assuming they told us the truth. Were you drunk at least once last week, right? And the answer that they got is going to be called P hat, and it wasn't 12%. In my sample of 100, it was 14%. Could you imagine that could happen, right? You ask 100 people, 14 out of them said I was drunk last week. Why is it not 12%? I mean, that's the real answer, right? Why do you not get a perfect match? It's just randomness, isn't it? Just depends who you ask. Can you ask a couple of people who'd like drink a little bit more? No. When you take another sample of 100 different people, and you find the proportion of them that was drunk, would you expect the second group of 100, right, 100 different people, would you expect the same percentage, right, 14%, to be drunk? In other words, should my second sample be the same number as my first? What do you think? No, there's no reason it could be, right? But isn't there probably more likely that it'll be close to it, but a bit different, right? And it ended up being, in my pretend story, it ended up being 11%. And then you do it a third time with 100 different people. And this time you nailed it. And one more time, you did it fourth one of 100. And you got. So can you imagine that each time you take a sample of 100 people, isn't there going to be some variation in the answer, right? They're not always going to agree with this number. Would you also agree that these numbers should be at least close to that number? So what is a sampling distribution? In this case, for a proportion. Well, it has been found that if you did this process of picking 100 random people and getting the p-hat, and you did it theoretically for thousands upon thousands upon thousands of times, and you made a histogram of it, it ends up looking like this. Have you seen data that looks like this? Yeah. In fact, isn't that a normal distribution? And this is called the sampling distribution, because the numbers in it came from samples. Right in the center, the kind of number that happens more often than any others, right? Right in the center. What value of P do you get technically? What value P hat, but what value do you get here? What would you expect that number to be? Does that seem reasonable that if you do lots and lots and lots of samples, you get lots and lots of different answers? But does it also seem sensible that you should get the most common answer should be that guy, right? Or at least close to that guy. So a sampling distribution is a normal distribution with the guy in the middle equal to 0.12. Seem reasonable. Now we would call that, I know it's a little bit of a contradiction, but we call that the mean. So the mean of a sampling distribution, even although the numbers are proportions, it's the mean of them because there's lots of them, right? Is 0.12. It's the population value. Less obvious is the standard deviation of the sampling distribution. And the standard deviation, well, it's got tons of names. Which one will I use? Well, I'll use the one that's most common, SEP hat. And that is standard error of sampling distribution. The standard error, SEP hat, the standard error of the sampling distribution is a standard deviation. You remember the guys that go 1, 2, 3, 1, 2, 3, right? The normal standard deviation. It's called standard error. That's what they call it, so that's what we have to call it, right? But it's still a standard deviation. And it has a formula. The standard error of the sampling distribution is the square root of P, 1 take away P over N. So there's a little formula for today. So put it all together. Sampling distribution for a proportion is normally distributed it has a mean of P. It's gonna, I guess I should use the word mean, that's better. There's a mean of P and a standard deviation called SE, which can be found by doing P 1 minus P over N. So if you took lots and lots of samples of 100 from a population where the P value is 0.12, you would get lots of answers, many of them close to that, but not all of them. But the average of all of these would be 0.12, and that the standard deviation, called the error, is found by this guy. So in this story here, the mean would be 0.12, and the standard deviation would be the square root of P 1 minus P over N. So that would be the square root of 0.12 1 minus P is what you get when you take this away from 1. So that's 0.88. And it's all divided by the sample size of 100. So I've got the square root of 0.12 times 0.88 divided by 100. And the answer I get here is 0.03, rounded off. So if the percentage of Scots people who were drunk was 12%, and I took samples of size 100, this is what all those samples would look like if you just kept on doing it forever and ever. This guy is 0.13, so that's 15. 18, 21, 9, 6, 3. So 1, 2, 3 standard deviations away from the mean. 1, 2, 3 standard deviations away from the mean. Now, how can this actually kind of be useful? How can understanding what a sampling distribution is like, how that can be put into effect? So let's give you a new story. Let's suppose that you've got a big machine and it makes computer chips. And no machine is perfect because some of the material that you put in has got bits wrong with it, right? And so we know that this machine has a failure rate of 3%, right? So when they come off the line, 3% of them are not working, right? They put them in little testers, right? And they test them, right? That's what this machine should be. So from time to time, you take a sample. Let's take a sample of 50 of them coming off the line, right? And find out how many are defective. And we found out that our p hat is a sample of 50. Let's suppose that 10 of them were defective. So what's that? A 20% defective rate. Would you be worried that this machine is maybe not working the way it used to? That 20% are defective, where it's, you know, you're going to have some that don't work. It should be 3%. But couldn't that just be an unlucky sample? Because maybe the next sample, I only get 1 that's wrong, right? Or 2 that's wrong, right? So how can you check it? Well, you can create a sampling distribution pretty quickly. We know this number is 0.03, right? I know what the standard error should be. It's the square root of p, 1 minus p, divided by 50. And so I'm going to go square root of 0.03 times 0.97 divided by 50. And the answer I get is 0.02. And if I go here, I get 0.05. If I go here, I get 0.07. And if I go to here, I get 0.09. Can you see that 20% is way over here? What is special about a number that's bigger than 3 standard deviations?
It's an outlier.
It's an outlier. In fact, in this particular case, isn't this? Yeah, you better stop that machine. It's got something wonky in it, right? The soldering gizmo is only working to half efficiency. In fact, now that I've built this, don't I now know that anything bigger than 9% is a warning sign that you've got problems? So when the guys who do the quality analysis thing and they're taking some things off the line, and in some cases it's destructive testing, right? Suppose you're making bars and they should have a certain amount of strength, right, before they snap, right? Well, the only way you can test that, isn't it, by snapping them, right? So you would be able to, that's called destructive testing, right? So you should be able to have a kind of range of values. Well, on this side, it would be nothing wrong, right? And anything that doesn't fit inside that range of values, right? The guy we would call outliers. Those are the warning sign ones. So there's one of the uses. And unfortunately, this is us. So if you just came in and you missed a comment I made, while I'm kind of doing this, you can do your last name for attendance. Your report has been sent out, so you should be able to see everything that I have, check it for accuracy. If it didn't arrive, send me an email with the email you'd like me to use and I'll change it over. And that is us for today. Bye-bye. If there are any questions, I'll hang about. Otherwise, I shall see you tomorrow. Carson, Gloria, anybody, David, any questions? If not, bye-bye. Okay, I'm out of here.